Hello, my name is Mason Cipollini, joined by my lab partners Colin Brown and Leif for Lab 1 of OPTI 471B. This video will cover the procedures and results of our experiments surrounding kinematic design and Gaussian beam alignment. Our initial experiments for this lab involve the basics of laser alignment. To start, we first inserted a 633 nanometer wavelength red laser into the kinematic mount. This mount would be attached to a horizontal translation stage affixed to the lab table. Next, an optical rail would be affixed to the table vertically parallel to the intended beam path. A pinhole aperture would then be attached to a rail carrier via a post and post holder, and this assembly would be placed along the rail. Once all was in place and the optics were adjusted to an approximate height of 200 millimeters above the rail, laser alignment could begin. To do this, the pinhole would be slid along the rail until close to the laser. Horizontal and vertical adjustments would be made using the micrometer on the translation stage and the height adjustment knob on the mount's post until the laser traveled fully through the hole. Then, the aperture is slid to the far end of the rail where the mount's fine adjusters would be utilized to achieve similar results. This procedure would be repeated until the laser traveled cleanly through the pinhole at both near and far views. Once this is achieved, the laser is aligned. Next, we would need to verify the laser's level and alignment. To verify the level, a pentaprism affixed to a tilt stage would be mounted in the beam path via a right-angle post assembly and rotated until the output beam is reflected 90 degrees downward into a glass of water. From there, we would use the fine adjusters on the stage to compensate for any imperfections in the prism and observe the stability of the back reflections. Since ours did not fully align with the source and had instability with physical activity on the table, the setup was not level with respect to gravity, likely due to the table itself. To verify the alignment, we would affix a second rail 90 degrees to the right of the original onto the table. Then, a beam splitter cube would be placed at the end of the first rail with the reflecting face pointed towards a second pinhole aperture on that second rail. Since both pinholes are at the exact same height, if the beam goes fully through the second hole, our alignment is verified. This test would be repeated with the pentaprism, where the output would go towards that same pinhole. When doing this test, we saw that the beam coming out of the cube beam splitter depends on the rotation of the cube beam splitter with respect to the beam, meaning that you have an additional degree of freedom to align. The pentaprism always outputs exactly perpendicular to the input beam, and you only need to align 1 degree, the rotation about the beam. Using the pentaprism is more convenient for getting a perpendicular beam.
The goal of this section was to align a second green Heine laser to be parallel to the table and parallel to the first red laser beam, and subsequently co-align the two beams such that they overlap in space, creating an orange spot. First, the new green Heine laser was aligned identically to the first laser such that it was parallel to the table. To co-align the two beams, a pentaprism was placed in the beam path of the green laser and a cube beam splitter was placed in the beam path of the red laser. The prism was oriented such that the green laser hit the reflection face of the beam splitter. The final combined beam exited out of the transmission face of the beam splitter. The X and Y position of the green laser was adjusted until the two beams overlapped in space after exiting the beam splitter, forming an orange spot on our target.
In this section of the lab, we aligned positive lenses along the optical axis using kinematic mounts and the laser. The lab handout requested us to use several different lenses, including plano-convex, biconvex, and plano-concave lenses. Unfortunately, only 2 plano-convex lenses were available, one with a 300mm focal length and one with a 200mm focal length. To begin, we aligned a single 300mm lens with the previously aligned red laser and rail. The lens was already mounted in a tip-tilt kinematic mount, giving X and Y rotation. This was placed in a post holder on a translation stage in the X direction, with Y translation being provided by the post. Then, the retroreflection from the flat surface was sent back into the laser cavity using tip and tilt adjustments, and the retroreflection from the convex surface was adjusted using X and Y translation. The next part of this section was to create a Galilean telescope, but with only positive lenses available, we instead made a Keplerian telescope. The original lens was left in place, and the new lens was inserted after, being the final element in the system. The same adjustments were made to align the element to the optical axis. Although the path was slightly altered due to the double pass through the first element, when the second lens is correctly aligned, its surface reflections both pass into the laser cavity. Finally, the spacing of the lenses were adjusted to create the telescope, and it was verified that all retroreflections passed back into the laser cavity. In this section of the lab, we align a microscope with the optical axis, then use it to align a lens inserted in the optical path. To begin, with only the laser in the system, a target is placed at the end of the optical path, and the spot of the laser is marked with a pen. Then, the microscope is inserted in a tip-tilt kinematic mount, which is then mounted on an X-translation stage using post holders. This again gives us 4 degrees of freedom for adjustment, along with Z-translation along the optical rail to use in alignment. First, a rough alignment was done such that the laser entered the microscope objective and an expanded beam could be seen on the target. Then, tip and tilt adjustments were used to correct angular misalignment. This appears as the expanded beam walking across the image plane as the microscope is moved axially. By adjusting tip and tilt, the expanded beam does not move laterally, only expanding and contracting as the microscope is moved along the rail. Then, X and Y translation of the microscope is adjusted to center the reticle and expanded beam on the previously marked location, ensuring the laser passes through the center of the optics. These 2 steps were repeated at different locations along the rail until the system was fully aligned. In this alignment process, we discovered a flaw in our optical rail. It may be hard to see in the video, but the rail appears to have a misalignment somewhere around 1/3 up the rail away from the laser. This can be seen as a stable alignment in the latter 2/3 of the rail, with an abrupt jump and a new stable position in the closest 1/3. This was confirmed with the TA as an issue with the rail and not our alignment. For the last part, the microscope was sent towards the end of the rail and a lens was inserted. This lens had the same kinematic mounts and degrees of freedom as the previous part of the lab. An initial alignment was done using the retroreflection technique previously described. We then verified the alignment by moving the lens along the rail and observing the image on the target. We found the image did not move and the lens was already correctly aligned without needing further adjustments.